everybody. My name is John Sexton, and I will be presenting on biomechanical systems and assistive technology with eye tracking to you all today. And the goal of this lab is to learn how hardware and software can combine to solve the problems for folks who can only communicate with their eyes or have limited mobility, so that we can create assistive, inclusive engineering solutions for them. So first step to any engineering project, obviously, is to identify the problem, which I'm sure you all are familiar with. And for this problem specifically, we want to look at folks who have a variety of medical conditions, such as ALS, or you've probably heard it also called as Lou Gehrig's disease, cerebral palsy, people with stroke. Anybody in a wheelchair that has limited mobility kind of is the bucket of people that we're falling into here. And we're looking at those who have a loss of motor control or speech. So take ALS as a specific example. You lose the ability to move, you lose the ability to speak, and eventually you also lose the ability to breathe. So having accessible solutions as you progress through losing all of that ability is really important to quality of life, independence, and wanting to keep fighting. There's a lot of technology out there, but it's always improving. And so we want to make sure that we are consistently thinking about this so that there are always accessible solutions for folks. And I am excited to talk to you about this today because I have familiarity with this problem firsthand. As you can see here, we'll play this video for you in a second, but my father has ALS, and so my family and I worked on developing a solution that allowed him to control his power wheelchair with his eyes. He can't move, he can't talk, and he's also on a ventilator that helps him breathe. But this is one way where he can still have his independence, he can still have control, and keep his quality of life high as he battles through ALS. My dad was diagnosed with ALS in 2014. That diagnosis was miserable. I mean, I was 13 years old. I don't wish that on anybody. It was really difficult to see how his body was deteriorating, but you could tell that his mind was just going at 1,000,000 miles an hour of how to fix the problem.
I had an idea that could help people in my situation, but I needed my son's help to make it a reality.
Notre Dame student John Sexton is working with his father on assistive technology called eye driving, giving individuals who use a wheelchair the ability to control multiple functions with their eyes, granting them autonomy and caregivers relief.
Eye driving has given Sean a freedom that was gradually being taken away from him as this disease progressed. It improves his quality of life. It improves his smile.
Our core mission is to improve quality of life and maintain independence, but we needed to figure out how to share eye driving with the world.
The Grand Challenge Scholars Program was developed at the University of Notre Dame to help students actualize their design and research interests into something that helps solve the greatest problems in our world.
Grand Challenges has been incredible. It's connected me to a peer team, faculty mentor, and business planning. The thing about the Notre Dame community, they don't want this to fail, not when so much good can come of this.
Working on this project has brought us together in a way that has given us life and has given us hope.
I'm so proud of my son, using his education to help others.
The University of Notre Dame asks, what would you fight for?
Fighting for the dignity of independence.
We are the Fighting Irish. And so you could see in the video, and you'll see again here, we're using an eye-controlled computer to control the wheelchair, to communicate, to control the remote on the TV. My dad's got his list of shows that he loves watching, and he uses the remote control that he can control with his eyes in order to go between all the Netflix and Hulu things. But here's just another example of somebody from their point of view looking on to an eye-controlled computer.
I look forward to seeing you all at the golf outing.
And so going back to the lab, we're going to teach you some of the basics and some of the considerations that you will have to make when designing technology for people who are going through these problems. And so the team of people, I don't know how much I could say I contributed here. There are some awesome folks who are also on the lab development team who we just want to give a shout out to, give a little round of applause to for all the hard work they put in here as well. So let's get started. We are going to investigate how to use hardware and software combined to communicate. And we're primarily going to focus on how we track the motion and gaze of the eye. And so the first concept to think about here is dwell time. So dwell time is how long you are looking at a certain point on the screen. And so you can see on the right here, when we are looking at this keyboard, the dwell time is how long you see that red box or that little circle that's closing in on the letter, how long your eye is staying on any of those given buttons, whether it's typing out words to communicate, whether it's going through a menu or going through a remote control, or even selecting directions to go with on your wheelchair. That all is controlled by dwell time, how long you are looking at a certain point on the screen. So let's test this out. Let's see how long we can get some first person experience here. I'm going to put on a 15-second timer, and I want you all to see how many of you can type out "how are you doing today" by looking on this screen. You can look at the letters to see if you can get this in 15 seconds. It is a little bit of an adjustment. It's something that you're not necessarily used to, but can give kind of a purview into the lives of the people that we're aiming to help here. So, all right. 3, 2, 1, go. All right. How'd you do? How did it feel? What was that like to have to look at a screen to communicate rather than simply very quickly say, "How are you doing today?" Something that only takes you, not even a thought on a day-to-day basis. And this ties into this next topic here. So we've had a little bit of an experience now as to what it's like to have to communicate this way. And the key thing, and the thing that's helped me, my family, our project the most, is knowing your user. To think like an engineer, it's really cool to build really cool things. It's awesome to build something that's groundbreaking, that's innovative. But if you are disconnected from the people that are actually using what you are building, then more often than not, you're gonna miss the point. And there have been certainly plenty of technologies that my family and I have tried that just hasn't worked. And it was actually out of necessity for those technologies that didn't fully consider the user that we created our solution. So for thinking about this user base, let's think about what movements can somebody do. With ALS, it's probably a little bit more limited, not being able to move their neck, not being able to move their arms or legs, their hands to drive the wheelchair. For somebody with cerebral palsy, that might be a little bit different. Somebody with stroke, that might be a little bit different. So thinking about all of the use cases rather than just the one is also helpful to develop an all-encompassing solution. And then what movements are impossible. So the other thing that we really want to avoid is when we are having an instruction manual or we're trying to teach somebody how to use our solution, we don't want to tell them to do something that they can't do. If you told my dad while he was trying to drive this, "Oh, hey, you need to turn your head 90 degrees in order to look at the screen," it would be inaccessible to him and it would be really frustrating because he wouldn't be able to do that. So we want to think about the limitations of the users as well as the limitations of our design. And then finally, using abilities such as eye movements to communicate and perform independent actions is something that we can take from different applications. So for this, we're saying as moving the wheelchair, but we can apply that to communication, to that TV remote. See how we can synthesize one technology and apply it to all sorts of applicable projects. Last thing before we jump into the projects here, just a little bit of history on how this technology has evolved over time. So all the way back in the 1800s, the very late 1800s, scientists began looking at naked eye movement and how the eye interacts with what it is looking at in its environment. And as we've progressed over time, we've recorded that eye movement, we've figured out correlations between what we're looking at and what we're interested in. And then now we've gotten to where we are today with eye tracking in real time, controlling technology that has a broad range of applications. So this has been something that is evolving up until this point, and it will continue to evolve after today. And that's why we're talking to all of you. Our two main tasks today are going to be to create a 3D model of eye geometry so we can learn how the eye tracking software works and how we can look at the gaze point, and we'll get into all of that in a little bit. And then we'll design a template for interacting with your environment. So driving the wheelchair, controlling a TV, controlling a thermostat, you'll actually get to, similar to how we just typed out how are you doing today, you'll get to drive a wheelchair with a template that you design. So how does this actually work? So we have this diagram over here that kind of explains in broad terms at a high level how this all tracks to see where we are looking at on the screen. So the first thing to point out here is the gaze point, which that's your letter on the keyboard, that's your direction arrow, that's your TV remote control option that's on the screen. So then imagine we have that H on the screen when we were typing, how are you doing? That line comes back to our eye. That's the gaze line. And that's one line that we use to calculate where we're looking on the screen. And that is defined by a gaze vector. So it's an object with magnitude and direction. The magnitude coming out of in the direction is coming out of our eye towards the screen. Our eye location is just where our eye is on our head. Pretty self-explanatory. And then the actual mechanism for tracking the differences between where our pupil is and where our gaze is, which we'll get to in a second, we use an LED and a video camera. So the LED will shine a light at the eye that will create a glint spot, and then we measure how far away that is from the center of the pupil. So, and we do that with the video camera. So if we take this image here, and we'll blow it up in a second, we have the glint spot here, we have the pupil here, and there will be a vector in between those 2 points. Looking at it a little bit closer, we see the glint spot here, which is from that LED, usually is infrared light that we use here. And then in this pupil, we have that center, and then we have the vector, again, object that has magnitude and direction to calculate where we're looking at on the screen. And I'll explain how that happens in a minute. To go more in depth, we're going to talk about the pupil center corneal reflection, PCCR method, and it's exactly what we just walked through. You have a camera image of the eye that we had from that video camera underneath the screen. We have the light shown, we can see our glint spot, we can see our pupil. We have the center of the pupil, we have the glint spot, we have that pupil glint vector that we were talking about before, and then we have our computer. So the computer saves a lot of these different vectors, and it compares what it tracks with the camera to what it has saved in the system. And so if it finds a match, that's how it can control where the cursor is on the screen that indicates where we are looking, and so that it's more accurate. Now, where do we get all of these vectors? Well, we have to calibrate. So you look at 5, 6, sometimes up to 9 different points on the screen, and that gives baseline vectors for the system to use in order to track where your eyes are looking. So from those points that you were looking at on the screen, you can figure out just about anywhere else that you're looking. Now, calibration is important. Sometimes it's difficult to calibrate some systems as opposed to others, or if you have glasses, sometimes the glare has an effect. But for the most part, you're able to use this to get these stored vectors and identify where on the screen that you are looking. So now we are going to create our own 3D model so that we can kind of visually see this and have a little bit more of a hands-on experience to understand how this tracking works. So one thing to mention before we get into it is some of the geometry involved, and specifically talking about the gaze offset angle. So that's showing the up-down angle that we see here. You can see the camera is included here, and then this angle right here is where this offset angle is based on our gaze direction. And to test this out a little bit, we can go to this link, which I already have open here, and you can move this pupil around to see what the different angles are and to see what this glint vector, pupil glint vector, might look like based on where the pupil is in relation to this glint spot. So if we're looking down, we can see this glint vector is here. If we're looking up, this glint vector is here. And you can play around with that a little bit more if you'd like to. Okay, so now we will create the 3D model. So primary goal here is to define the eye geometry, and we will do this by using some pipe cleaners, some styrofoam, and a clear plastic sheet. So I want to make sure we define where the pupil is, where the glint spot is, and where the glint vector is, and we can, after this is all defined, look at what our angles are. So we'll have our horizontal angle here and our vertical angle here, the gaze offset angle here. And once you determine what the glint spot, the pupil, the angles, the vector are, then you can have a visual representation of what this eye tracking looks like. So here are a few examples of how some folks have done this in the past. You can see we have the pupil defined here, the glint spot here, horizontal angle here, vertical angle here, the gaze point where you're looking at on the screen, where the light is going to be shining. This little styrofoam here is our camera, I guess, and this purple pipe cleaner is the LED. So get creative with it. Do what you want to in order to understand how this eye tracking works. So I know there are a lot of moving pieces, a lot of different colored parts, a lot of different things to think about here. But remember, we're just trying to understand how the eye interacts with the screen. So if it gets super complicated or there's a lot of things to understand, just remember at the core of it is we're just trying to understand what we're looking at. So now that we're done with that activity, let's move on to applying this technology. So we are going to create different ways to drive a wheelchair through some mazes and see how this eye tracking technology applies beyond just looking at a screen. So before we jump into this activity, want to give some background again. So my family and I have been working, as you saw at the beginning of the presentation, on this project called Life Drive. And they called it iDriving in the video, but we call it Life Drive now. And what we're doing in this lab is essentially what my family and I did with Life Drive, where we're taking existing technology that we understand or are grasping the concepts of and applying it to a real world example where there's a gap in assistive technology, where the solutions that were out there for my dad didn't work well enough for him, so we needed to build something ourselves. And so that's what we are doing here. We are taking eye tracking, which is a really cool technology, and we are finding other ways to apply it to make accessible technology for more people who need it. Now that we have the background, now that we've gotten our feet wet with eye tracking technology, let's see if we can connect some of what we learned to what we're going to be working on here. So we have these different pupil glint vectors here, and they're associated with a direction. Now we'll be looking on a plastic sheet that has these arrows, but what's happening in the computer? Well, let's see if we can match what we have below. Which direction, what command are we going to do if the computer sees that this is our glint vector? If you said stop, that is correct. Good job. That is what you would do if the computer and the camera picked this up. So now that we saw one of these matching commands, let's do a string of them together. Maybe we can drive through a maze. So if we look at this, what direction would this be? Right, Right. It would be going right. And then this one be going forward. Yes. This one, right again. And then what would be this last one? Going left. Awesome. You just drove through a little bit of a maze. Sometimes when you are driving through hallways, going through cul-de-sac, going for a walk, kind of navigating in between people on the street. This is how you think sometimes when you are driving. When I've been in a power wheelchair before driving, I've been thinking, oh, forward, left, right. Sometimes that's just programmed. The programming from the computer can sometimes go into your brain. So good job. Now let's do some more work in this activity to translate these eye gaze into wheelchair movements. So our objective here is to help a user interact with their surroundings, interact with their computer, and create a controller template to have that be what the user uses to have their eye movements control their imaginary power wheelchair in this instance. So what you will be doing, you will create the template. You'll use these clear sheet protectors to draw out an example template of what you can look at, some arrows, maybe a stop button. Determine how many different directions you want. Do you want just cardinal directions, or do you want a forward left, a forward right, reverse left, reverse right, stuff like that. And then consider number of units to travel based on what mazes you use, what floor plans you use, or just kind of what you have been, what you think would be most useful to the end user that you are designing this for. So here's some examples of templates. I will say the middle one actually looks fairly similar to what we have for Life Drive, but you can also have a template like on the left here where it's just forward, reverse, left, and right. I would advise having a stop button. You want to be able to stop the wheelchair at any time. You don't want it to go out of control. So if you put a stop button in, I think that would be a good idea. And this one on the right here, you can have 1, 2, 3, 4. Those are maybe blocks in the maze. So, if you select 1 and then you hit forward, then you go 1 block forward, and then you select 2 and turn left, then you go 2 left, stuff like that. And here's how you're going to set up this experiment. So you're going to get into groups of 3 or 4, and you're going to define a few different roles. So you'll have a user, so the person that's actually looking at the floor plan maze and makes the eye movements towards the template. So you're going to look at where you want to go and then make that corresponding decision with the template. Then you'll have the engineer who will interpret those gaze points and figure out where the user is trying to go. And then finally, you'll have an observer or a recorder. They will look at both the user and the maze along with the engineer, and they'll record how many correct movements are made as you traverse through the maze. So based on what the engineer records that the user is looking at, we'll see what is correct versus incorrect. So here are just a couple of examples of mazes, floor plans that you can use to see where you're going to go and try and traverse through all of this. So have fun with it, see how you can go. And then once you've gone through these mazes, you can record your results, calculate your results. So measure the distance between the user and the template, the engineer and the template, track the total moves that it took for you to get through the maze, track the total number of correct moves. You can even time yourself, have a little bit of a race. In real life, racing is not necessarily the safest thing, but in this imaginary scenario, time yourself, have a little fun with it. And then after you find the number of total moves and correct moves, calculate your accuracy and make some notes as to which types of mazes you used, how did you define your template, and how do you know how many steps to move, stuff like that. Those were just 2 things to consider when creating this sort of technology. There were plenty of other things we had to consider, but the biggest ones mainly were how long is our dwell time? What is it going to look like for duration of commands to send the chair forward, backward, left, right? And how does that interface set up? We're still making changes to our interfaces to this day. They are always changing. You can always be improving. That's the engineering process. So now that we've moved through that segment of the activity, just want to point out some other assistive technologies, some other things that are out there. So there are plenty of other assistive technologies using eye tracking, not using eye tracking, that can apply and work for people, these people that we are trying to help here, this patient population. And so in the Internet of Things, you can think about anything that uses technology, that thermostat control, that TV remote, that communicator app. All of that can be integrated for an assistive technology solution. Another thing is AI. So one really good example of this is voice banking. So my dad, for example, has a lot of audio files of him speaking and various videos and various other media. And so we took a lot of those audio files, sent it to a voice banking company, a voice banking software. They plugged it into a machine learning module, and then it popped out a computerized version of his voice so that he can continue to use his voice through his communicator app. So he doesn't completely lose his voice, even if he can't talk anymore. And then finally here, car adaptations. So we have different ways to control a wheelchair, but there are also different ways to control a car. So we have a really good family friend. His name is George. He had a stroke and he's in a wheelchair, but he still drives his car. Now it looks a little bit different. Some of the seats are taken out. His steering wheel looks a little bit different. The gas and brake pedals are not exactly the same, but there are modifications that have been made that allow him to still drive around. And in terms of other uses of eye tracking specifically, there are eye tracking glasses, and sometimes you can see this technology also in cars where it monitors your alertness based on what it's tracking in your eyes to see if you're drowsy or see if you're falling asleep at the wheel, which can be an added safety benefit. Right eye, which actually tracks as you read something on a screen, can actually help a lot of folks that have dyslexia or learning disabilities, where you can kind of get a better sense of how they are reading or how they are processing information that is put in front of them. And then vision therapy is another application as well. All right, and that is the main portion of the lab. So thank you all for joining us. I hope you learned a lot. I hope you had some fun, and I hope you saw how technology can benefit and do good for other people. It enhances the experience of the engineer as well as the folks that the engineer is serving when a project that you're working on is for the greater good. So I hope you all had a great time, and we'll see you later. So now we're going to do 3 extension activities for those who are still with us, and we're going to start with creating an E-Tran board. So we did a system where we figured out how to drive a wheelchair through a maze, and we used that plastic sheet. We drew our interface on there to do arrows and stop buttons and all of that. But now we are wanting to create a communication system, essentially. Very similar, just a different application. So let's start with defining the problem. So let's take some time to think about with your team, with your classmates, why is it important and what are we trying to solve with developing this solution? What are we trying to do for folks who can't communicate verbally anymore? After you take some time to define your problem, let's do some research. Let's look at possible keyboard configurations and layouts to create something that somebody can look at with their eyes and still be able to communicate. Then we'll design the layout, we'll build the board, and we'll test it and analyze the results. So to design and build the board, we'll use the clear plastic sheets just like we did before for the power wheelchair simulation. And then we'll create a procedure for interpreting what somebody is saying. So here are some things to consider. And also consider that, like we did at the very beginning when we typed out, "How are you doing today?" it's going to be a little bit slower than what you're used to for communicating. So think about the size of the letters, the positioning of them, any special instructions for interpretation, what letters are most commonly used, what phrases are most commonly used, all of this sort of thing. Maybe even trying a calibration exercise, all of that to consider when you're designing and building your board. So as you're considering all of that, here's an example. So Dixon, another one of the people that was working on developing this lab, has eye gaze. It's an eye-controlled computer, has an interface like what you're about to build. Here you can see all these different apps that you can select, and you can think about, okay, so we have some rectangles here. We have large text to be easy to hit while we're looking on the screen. We have a home button, we have a pause button, all this sort of stuff. Different things to consider here from a real life example. And some non-real life examples here as well. You can think about the different design choices you can make while making this eTran board. So in this top left one, maybe we go with phrases that are very familiar or common that you say throughout the day. Instead of typing out, how are you doing today? Maybe that's something that's saved onto your system already. In the top right, maybe you want to go between different screens and have those screens be larger text or larger characters to choose from. So all of that sort of thing as well to think about. Then you have some other options like a standard keyboard even in the bottom right. So how are you going to test this? Well, similar to how we had the user and the engineer, we'll have the reader and the writer here. So the reader will face the eTran board and use their eyes and the keyboard to answer questions, communicate, write out a phrase, whatever you decide you want to type out. The writer will be on the opposite side of the board and will attempt to interpret what the reader is looking at. And then you'll keep track of the accuracy of interpretation and see how much of what that person is looking at you can write down correctly. So you can do some test words or sentences, record what the guesses are, calculate the accuracy, and make any notes or observations. How hard was it to interpret this? How accurate was this? How slow, how fast were you able to pick up on how to do this? All of those sorts of things we want to collect and analyze our data here as well. So for our second extension, we are going to go back to that PCCR method to see for ourselves a more dynamic version of what we did in activity 1 of the main portion. So to have this dynamic visualization of what happens with eye tracking, we're going to experiment with a few different creative things. So we're going to build a mechanical model of the eye and we'll flash a light on it and we'll see what happens. So using either a ping pong ball, a small ornament, some small round object, that will simulate the corneal sphere. So that'll simulate kind of the sphere of your eye. And then we'll get a black magic marker, some black pen, and draw a pupil. And then the light will flash on for our glint point. Pretty straightforward to build the model. You can use the marker to draw the pupil with a small but noticeable diameter on the ornament or ping pong ball. Then with one hand, you'll hold up the pupil and the other, you'll hold up the flashlight and you'll be able to see where that glint spot is depending on how you angle the sphere. So we're not recording anything here. We're not tracking anything, but this is more so that you can see how the glint spot, the vector, the relation of the eye to the light and the pupil to the light changes as you move around. And for our third and final extension, we get to do some of the actual math for the geometry involved with eye tracking. This is this diagram here again where we're looking at where the gaze point is and what that is in relation to the pupil, the glint spot, and all of the vectors and angles involved. So eye tracking technology uses complex geometric algorithms to determine exactly where we're looking on the screen, but geometry can help us get a general idea. And so the information that we collect from the camera that's looking at the light shining on the eye informs us of where all of these lines, these vectors, these angles exist. So we have two angles primarily that we want to look at. The gaze offset angle, which we're going to call angle B, and then we're just going to call it the angle A. So I referred to this earlier as the horizontal and the vertical angle. So if we look at A, we're going to see that's the horizontal angle. It's how far off to the left or the right we are with our glint spot from the center of the pupil, and then the gaze offset angle up and down. And we can see that we get two right triangles when we try and calculate these two angles. You can see here we have a hypotenuse, that is the radius of the pupil. And we can see here we have a nice little right triangle relative to where the glint spot is to the center of the pupil. So reviewing right triangles here, Pythagorean theorem, everybody's favorite theorem. A squared plus b squared equals c squared. So you have the hypotenuse, which is c. We have the angle. We have a, which is our adjacent side, and b, which is our opposite side. And that brings us to SOHCAHTOA, which allows us to calculate this angle based on which sides we know. So for sine, it's opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. So now let's do some actual calculations. So figuring out the glint pupil vector. So if we look in image number 2, we can see that light blue line is telling us what the glint pupil vector is from that glint spot to the center of the pupil. We aren't considering the gaze offset angle just yet. And so using these example numbers, we can calculate what c, the glint pupil vector, is. So a squared plus b squared equals c squared. 3 squared plus 4 squared is c squared. We get 25, and the square root of that is 5. So we have a glint pupil vector length or magnitude of 5. Now, computing the gaze offset angle, we have the radius, which is 7 millimeters, and then we have the change on the opposite side as 4 millimeters. So what would we use to calculate this? What do we know? We know the hypotenuse and we know the opposite. So we can use sine to calculate this. And so if we have sine of b is 4 over 7, we can do inverse sine in our calculators, and we get an angle of 34.85 degrees. So here are just some other resources. If you liked today's breakout and you like other types of engineering related to today's breakout, here are some additional things you can look at. Thanks again for joining. I hope you guys enjoyed it. I hope you had some fun. And I hope that you can take this with you in any future engineering projects that you work on.